Let's talk about some of the properties of the normal probability distribution. We already know that the area under the curve from A to B is the probability of x falling between A and B. We also already know that the total area under the curve is 1, and therefore we have half the area on each side. One thing we've not talked about is the fact that the probability of x being C is 0. If we consider a normal curve, and C is some value of x, we want to figure out the area that is directly above C. So we're looking at this area here. However, to find the width, we would take the upper boundary and subtract the lower boundary. So in this case, our width is 0, and therefore our area is 0. And therefore, the probability of x being equal to C is 0. Now, when we say that the probability is 0, we are saying that that's an impossible event. If, for example, our normal curve had to do with the heights of people, and C happened to be 6 feet tall, can we say that being exactly 6 feet tall is impossible? No, we cannot say that. It's certainly not an impossible event. What we need to do is keep in mind that our normal curve is a representation of the actual probabilities. It's the best model that we have. However, this model has the failing that when we have exact values like this, it implies that the area is 0, which is not true. We don't want this to be an impossible event. And so what that means is that we're only going to use the normal probability to discuss probabilities of x falling within a certain interval. We do not use it to discuss the probabilities of x being equal to a certain number. If we were looking at that, we would be talking about a discrete probability distribution. So we're only going to consider intervals. And we have to realize that that's one of the failings of our model when we use our model to represent a real-life situation. Notice this last fact, the fact that the probability of x being equal to C is 0, means that it does not matter whether we include the ends of our interval or not, because the area directly above that A or that B, that boundary, is 0. So therefore, all of these, whether we include one end, both ends, or neither end, all of these are the same due to the fact that the probability above the probability of x being a particular number is considered to be 0. Let's move on. Here's another example. Let's suppose that Dusty Dog Food Company ships dog food to its distributors, and it ships the dog food in 50-pound bags. When you purchase dog food or something else in a 50-pound bag, you can be pretty sure that the weight is not exactly 50 pounds. It will simply be very close to 50 pounds. Here, the weights of our dog food bags are normally distributed with a mean of 50 pounds and a standard deviation of 0.5 or half a pound. If a bag of dog food is selected at random from a shipment, what's the probability that it weighs more than 51 pounds? So first of all, we need to know what our mean and our standard deviation are. 50 pounds and half a pound, or 0.5. If we want to find the probability that it weighs more than 51 pounds, we're going to draw ourselves a little sketch. Our mean is 50. So if we're at 51 pounds, that means we want this area to the right of 51. If we are at 51 pounds, how many standard deviations away from the mean is that? Well, one standard deviation is a half pound. Therefore, if we're 1 pound away, we are 2 standard deviations above the mean. You can also do this using your formula, of course. Your z-score is going to be x minus mu over sigma. So 51 minus 50 over 0.5. Sorry, make that 0.5. Which is 2.0, as we already noticed. So we look up z of 2.0 in our table, and we find that our area is equal to 0.4772. Now this is the area that we want. That's not what we just found. What we would need to do is this area that we want is going to be equal to, we don't have areas of that shape in our table, but we know that this will be 0.5, and then from there we can look up the area that we just looked up in the table would be this area. We'll call that A1. And so my probability that x is more than 51 pounds, that's going to be the probability that z is more than 2, meaning I'm more than 2 standard deviations above the mean. And so that's going to be 0.5 minus A1. So 0.5 minus 0.4772, which is 0.228. Sorry, scratch that, make that 0.0228. That's the area that we want. And therefore, that's our probability. Let's look at the next one. Now we want the probability that the bag of dog food is less than 49 pounds. Okay, so once again, if we look at our sketch, 49 pounds will be down here. And so now we're talking about the area out in the tail. We do not have areas of that shape in our table. So what we're going to do is we're going to notice that if I just look at half the curve, everything from 50 to the left, that's 0.5. And then we're going to subtract off the area between 49 and the mean. In other words, this area. Now, my z-score is -2. How do I know? Well, I know that when I was 1 pound above the mean, my z-score was +2. Therefore, if I am 1 pound below the mean, my z-score will be -2. You could put it into the formula, but you're going to get this just by the symmetry from part A. The left and the right halves of our curve are going to look exactly the same. So that area, once again, if I call this area 2, area 2 is also going to be 0.4772, just as in part A. Okay, and so therefore the probability that x is less than 49, that's going to be the same as the probability that z is less than -2, which is going to be 0.5 minus 0.4772, which once again is 0.0228. Exactly the same as in part A because of symmetry. Now for the third part of the question, let's look at the area between 49 and 51 pounds. Once again, we're going to look at the symmetry. Okay. So between 49 and 51 pounds, so my mu is 50. So 1 unit to the right, then 1 unit to the left. So we want this area in between. And this is going to be equal to this one plus this one. But we already know that this first area was 0.4772. And then also the second area is 0.4772. So we're going to add these up, or you could just multiply by 2. And you're going to end up with 0.9544. And what is all this equal to? This is the probability that x is in between 49 and 51. Now, if you recall, our standard deviations for 49 and 51 in both cases were 2 and -2. So this means that if we're between 49 and 51, we are 2 standard deviations from the mean in either direction. Okay, now look back to one of our facts about normal distributions. If we go back a few pages, here it is. Look at this. 95.4% of our area is within 2 standard deviations from the mean. That's what we just discovered. And so it's helpful if you can remember these numbers. And often you can use this 68% for within 1 standard deviation, 95.4 within 2, 99.7 within 3. A lot of times we can use that to check if our answers, even if we're not looking at exactly 2 or 3 or 1 standard deviations from the mean, we can look to see if our answer seems to be reasonable. Okay, let's move on. Let's do another example. Let's go back to where we were. Okay, so we just finished the dog food problem. Came up with 0.9544 between 49 and 51 pounds. So now let's try this one. Let's suppose that we have a certain hospital, and here the records show that the mean is 7.4 and the standard deviation is 1.2. We're talking about birth weights of babies. Mean is 7.4, standard deviation of 1.2. Let's find the probability that a randomly selected baby weighs more than 9.2 pounds. So once again, we draw our sketch. Drawing the sketch will really help you. 9.2 is above the mean. You want to make sure you get it on the correct side. More than 9.2, that puts us at this tail. here past 9.2. So we're going to find the z-score that goes with 9.2. And so that'll be 9.2 minus 7.4 divided by 1.2, which is 1.5. And then we're going to look that up in the table. And that's going to tell me that my area is, let's call this area A1. .4332. Now what are we going to do with it? Well, we need to decide how to get this area, this shaded area. The way we're going to get this shaded area is we're going to realize half the area is 0.5. Then we're going to subtract that area that we just found, which is the area between 7.4 and 9.2, which I'm calling A1. So the probability that the baby's weigh, that the baby singular weighs more than 9.2 pounds. That's the same as the probability that z is more than 1.5, so more than 1.5 standard deviations above the mean. That's going to be 0.5 minus 0.4332, which is 0.0668. Now, let's find the probability that a randomly selected infant weighed less than 8 pounds. Once again, we sketch a picture. £8 will be just a little to the right of our mean. Less than 8 pounds will mean everything to the left. So that means all of this area. So we don't have areas like that on our table. So what we're going to do is we're going to break it up. We know that half the area is 0.5. And we know that we can look up the area from 7.4 to 8. We can look that up in the table. And then what are we going to do this time? This time we're going to add them, right? And we're going to have to take the half and then add a little bit more to get to our shaded area. Let's call this A2. So now we need to find the z-score for a birth weight of 8. And so that's going to be x minus mu over sigma. So 8 minus 7.4 divided by 1.2 gives me a value of 0.50. So we look up 0.50. In the table. And that gives me an area of 0.1915. So we combine them in the way that our picture describes. The probability of the birth weight being less than 8, that's going to be the same as the probability of z being less than a positive 0.5. This is going to be 0.5 plus A2, which is 0.5 plus 0.1915, so that gives me 0.6915. That's the probability that we're looking for. Now let's find the probability that a randomly selected infant weighs between 8 and 10 pounds. So here, so this time the 8 and the 10 are both on one side of our mean. And this is the area that we want. We haven't done one that combine the areas in this particular way before, so we need to figure out how to use the areas that are listed on our table to get this. The sorts of things that we can look up on our table go from the mean to a number, and that's all. So what I can do is I can go from the mean of 7.4 all the way out to 10. So that gives me this area, and then I can subtract the area from 7.4 to 8, and then that should give me the shaded area that I want. Does that make sense looking at the pictures? If we take the area from 7.4 to 10, we subtract off the part from 7.4 to 8, that will give us the area that we want. So let's call these, actually this one we already called A2 earlier, and we're going to call this one A3. So we have already found A2. Now we need to find A3. So we need to find the z-score that goes with 10. So that means we're going to do 10 minus 7.4 divide by 1.2. And so that gives me approximately 2.17. You're going to have to round to 2 decimal places to be able to look it up in your table. And so then we find that area 3 has to be 0.4850. Now from part B, area 2 was 0.1915, and therefore the area that we want, that'll be the probability that x is in between 8 and 10. So we're going to do A3 minus A2. So 0.485 minus 0.1915 gives us 0.2935. That's the probability that the baby weighs between 8 and 10 pounds. Let's do another example. Let's suppose that the GPA of a senior class of a certain high school is normally distributed with a mean of 2.7 and a standard deviation of 0.4. And believe me, the high schools do keep records of GPA like this. Mu equals 2.7, sigma is equal to 0.4. If a senior is in the top 10% of his or her class, and she needs to be in the top 10% in order to be eligible for automatic admission to a state university, what's the minimum GPA that the senior has to have in order to be certain of being eligible? Here's the idea. This time we're trying to work backwards from the area to the z-score. We know that our mu of 2.7 is exactly in the middle. We know that somewhere here is a value of x that we are trying to find. If this is the top 10% here, that means this area is 0.10, or our top 10%. Then what is this area? Has to be 0.4. Okay, because the entire curve, the area underneath it is 1, therefore the area underneath the top half is 0.5. So the 0.4 plus the 0.1 have to add up to 0.5. So what we need to do is we need to look in the table for a z-score that gives an area close to 0.4. Okay, and we've got two possibilities. If we have an area of 0.3997, this gives us a z-score of 1.28. This is from our table. And if we have an area of 0.4015, this gives me a z-score of 1.29. Let's figure out which one is closest. You could actually do some kind of an interpolation and get in between, but for our purposes, we're just going to pick one of these two. We're only going to choose a z-score out to 2 decimal places. So we've got two possibilities here. One of them, let's draw a picture. Here, remember the shaded area is what we want. If this is 0.3997, then here my area is equal to 0.5 minus 0.3997, which is 0.1003, which really puts me in the top 10.03%. Now, while this would get you very close to the correct answer, we don't want to use this because if a person was at the very bottom of this shaded area, in other words, if they were between 10 and 10.03, they would not quite make the cutoff to be eligible for the automatic 10% admission. So we're going to use the other area. Just because we do not want to risk falling below that cutoff. See, with the other one, if this area is 0.4015, then this little area, this shaded area, would be 0.5 minus 0.4015, which would be 0.0985. In other words, this would be the top 9.85%, which would certainly guarantee us being in the top 10%. So that's the one that we're going to use. But like I said, the first one will get you close enough that it would probably be close enough for most practical purposes. But we're going to use the second one. So we're going to use the z of 1.29. Okay, so remember that your x is going to be the mean plus z sigma. So this is going to be, what was my mean? If we go back up, 2.7 was my mean. So 2.7 plus 1.29 times my standard deviation was 0.4 of a point. So 1.29 times 0.4, which is 3.216. Alternatively, if you didn't remember this, remember that your z is equal to x minus mu over sigma. So you could put it in here. You could do 1.29 is equal to x minus 2.7 all divided by 0.4. If we multiply both sides by 0.4, we're going to get x minus 2.7. And so then my x is equal to 1.29 times 0.4 plus 2.7, which is 3.216. So our student needs a GPA of 3.216 to guarantee being in the top 10%. Okay, well, I hope this helped you get started with normal distributions. Good luck, and I will see you next time.